Okay, this is the second part. I've had to come back after eating some lunch. This is a second order example, so I've just done the first order example in the previous part. The method barely changes, you just need to basically reduce the system order before you begin. And the way that we do this is we change our aerodynamics. So before it was just E, but now we have to define a sliding variable to reduce the system order from 2 down to 1. And for a second order system, this is defined as E dot plus lambda E. And now we work through the exact same method, but instead of E, we use S. So first thing we do is we take the first derivative of S dot, like this, and it's going to be E double dot plus lambda E dot. And then the next thing is to identify our aerodynamics just so we know what's going on here. E double dot is equal to X double dot minus XD double dot. And if we were to multiply that by M, we would see that we can get M E double dot is equal to M X double dot minus M XD double dot. Great, because we have mx double dot. We just need to rearrange this equation. So let's rearrange this equation. Mx double dot is equal to minus c, subtract c, x dot minus kx plus u. And then we need to substitute this back into me double dot. So we'll give us m e double dot is equal to, I've already typed it out, so save a teeny bit of time and just copy that, mx double dot, which is this, minus mxd double dot, like so. Almost there. Now let's just substitute me double dot into our s sliding surface. So remember, multiply it all by s and we get ms dot is equal to m e double dot, which is great because we just found out what that is, plus m lambda e. So substitute in our me double dot here, like this, and also add this m lambda e. And now we need to design our controller u. The method I always use is feedback linearization, but we assume that we know m, c, and k. In reality, we don't for this sort of problem, but let's assume we do. U needs to be positive cx dot. There we go. Positive kx, positive m xd double dot, and minus m lambda e. I've just seen that I've made a small mistake here, that this is actually e dot. Earlier here we defined s dot as lambda e dot, not lambda e, so let me quickly update all of these so I don't lose track. Lambda e dot and lambda e dot. Cool. But remember, we don't know m, c, and k, so we can't make this controller in reality. What we have to do is we have to design a guess at our controller using assumptions for m, c, and k, called c hat x dot plus k hat x plus m hat xd double dot minus m hat lambda e dot, like this. Instantly we can simplify this. I'm not going to write another equation. We can instantly simplify this because we have m hat and m hat, so we can just do one instance of m hat, and it's going to be xd double dot minus lambda e dot, like that. Now the controller's good if we, remember, if we knew MC and K and we use this controller, our closed loop dynamics would be equal to 0. It would basically effectively cancel out exactly the MC and K in our aerodynamics, but we don't want that. We don't want it to be equal to 0. We want it to equal something that we can control, so a controller gain. So like I did for the first order, I added minus K0E, but we're not working with E anymore. We're working with our sliding surface S. So minus K0S is fine. I could add more terms. I could do K1 S dot and so on, but I'm not going to. You're welcome to, and it won't change your answer, and you can still prove asymptotic stability, but for now this is fine. K0S is okay. So let's substitute U hat into our MS dot. So it's going to look like this. I'm going to copy it out because it's going to get quite long here. MS dot and then U hat we can just copy like so, and basically replace the U term with all of them. So it looks quite complicated at this point, but again we're going to do that exact same trick where we use our definition of M tilde. I'm just going to do M, but I imagine this is the same for C and K. M tilde is M minus our approximation hat, M hat. So if we look at our M terms, we could first of all group this M times xd double dot plus lambda e dot. Although switch the sign because it's minus here, so it's going to be plus M xd double dot minus lambda e dot, which is exactly what we have here. And ultimately we can go through and cancel it all out. I'm going to start with C. We're going to get minus C tilde x dot, there's nothing crazy going on there, minus K tilde x, and then minus M tilde xd double dot minus lambda e dot e dot, like so, and then we have to keep our minus K0S in there, that's unchanged, and this is the simplified dynamics for M S dot. Cool. So next stage, to find a valid Lyapunov function, V, same deal, 1 over 2. Now look at the dynamics that we have. We have MS dot, but we're going to take the first derivative, and then we're going to sub in, so we want it to be MS squared. And that will give us MS dot S when we take the first derivative. And let's add our 1 over 2 gamma multiplied by all of our unknown terms, so M tilde plus C tilde plus K tilde, like so. And let's then just do V dot, and like I said, it's going to be M S dot, which we already have, which is good, times S, plus, and I'm going to separate all of these out now, so it's going to get quite long, frac 1 over gamma, and that's going to be M tilde times M tilde dot plus, and I can just copy these now. Save me having to write that out every time. C K, there we go. So that's our dynamics. That's the first derivative of the Lyapunov function done. Substitute in our dynamics. So v dot, big V dot, is equal to s times, let's copy and paste our ms dot, save some time. There we go, that's ms dot, and then all of these fractions, all of these are exactly the same, they're unchanged. So now, like before, we can group our C tilde, K tilde, and M tilde. So I'm going to start with M. What I'm also actually going to do is quickly, straight away, leave out the K0 S squared. That's just K0 S times S. And now let's group our terms. So first one is going to be M tilde multiplied by, well, the positive M tilde over here is 1 over gamma times M tilde dot. And then let's look at the negative. Negative M tilde is all of this. It's going to be, well, S on the outside. Remember, it's all multiplied by S. XD double dot minus lambda E dot, like so. Now we move on to C tilde. Let's look at C tilde positive. Well, same deal. It's 1 over gamma times C tilde dot, like so. And then the negative is just X dot S, which is nice and handy. Like that. And finally, K tilde, same deal, 1 over gamma times K tilde dot, and the negative is just XS, because it's just X multiplied by S. So now we're in the stage where we can design our adaptive laws. So adaptive laws, I suppose, because this is a separate video, I should show you where I'm getting this. So remember that I have already defined M tilde as M minus M hat. So M tilde dot is M dot minus M hat dot. Now, if it's constant, the derivative of a constant is 0, so M dot is 0. So M tilde dot is equal to minus M hat dot, and that's good because it means we get to choose M hat dot. It was a guess that we made. So these are our so-called adaptive laws, and we can design them such that these brackets go exactly to 0, and it cancels out all of the MC and K dynamics and just leaves us with K0 S squared. So, and we mustn't forget that actually M tilde dot, which is this one here, is actually equal to minus M hat dot. So when I design M hat dot to cancel out these dynamics, I need to remember that sign change. So M hat dot is going to be equal to, well, it's a little bit more convoluted. So it's going to be gamma first of all. That 1 over gamma times gamma will just be 1, so that will get rid of this 1 over gamma. Minus, if we want this to basically be positive, S xd double dot minus lambda E dot, we would just do this. It would be gamma S xd double dot minus lambda E dot, and this would cancel out these dynamics if this sign was positive, but it's actually negative now, so just put a sign change like that, negative. For that, that's the adaptive law for M hat dot. C hat dot is thankfully much easier. We're going to have gamma again, and it's just going to be XS, or X dot S, sorry, X dot S but remember the sign changed, so just put a minus sign there. That's c hat dot done, and finally k hat dot is simpler still. It's going to be gamma xs, but remember the sign change, minus. There we go. So if these are adaptive laws that we can make up. If we were to use these adaptive laws, these dynamics would make v dot go exactly to k0 s squared. And with this we can prove the stability. This k0 is a controller gain that we choose, and everything in s is known. We work out s using e dot plus lambda e, and e is just the difference. So we would need to measure our current state, subtract our desired state, and find that error, and then we're all done. We can get s. So that's as far as you're going to get with this. That is a first order done and a second order done. I think I will probably touch on adaptive control, neural network control, and I think that was going to have that will have to be a separate video. So annoyingly, this is turned into a 3-parter rather than 2-parter, but it is what it is. So I'm going to have to end this one here and do another one about neural network. So there we go.